3i Atlas isn't wandering aimlessly through our solar system. New orbital calculations show this interstellar object executing a precision approach to Jupiter's Hill radius with spacecraft-level accuracy, hitting a gravitational sweet spot 53.445 million kilometers from Jupiter's center with an error margin of just 60,000 kilometers. This targeting precision shouldn't exist in nature. When astronomers first detected 3i Atlas in 2024, they classified it as a standard interstellar comet, the third confirmed visitor from beyond our solar system. But trajectory analysis reveals something deeply uncomfortable. The object is threading a cosmic needle, approaching Jupiter's Hill radius boundary with the exactness of a planned orbital insertion maneuver. The Hill radius defines where Jupiter's gravity dominates over the Sun's pull. It's a sphere roughly 53 million kilometers from the planet's center, about the size of Mercury's entire orbit around the Sun. Objects inside this boundary feel Jupiter's gravity more strongly than the Sun's, creating a stable parking zone where satellites can maintain position with minimal fuel. NASA's own spacecraft aim for this region when establishing long-term orbits around Jupiter. Natural comets don't hit targets this precisely. They can't. Space rocks tumbling through the void for millions of years don't accidentally line up perfect approaches to specific gravitational boundaries. The math shows 3i Atlas maintaining its trajectory with an accuracy that mission planners at NASA spend years calculating for actual spacecraft. What makes this even stranger is what happened during solar conjunction, the 40 to 60 hour window when the Sun blocked our view of the object. When 3i Atlas emerged from behind the Sun's glare, it had experienced what scientists call a non-gravitational acceleration event. Something had pushed the object, changing its velocity in exactly the direction needed to refine its approach to Jupiter's Hill radius. The conventional explanation says solar heating caused ice to sublimate, creating jets that pushed the comet. This happens with natural comets all the time, but 3i Atlas shows an unusually symmetrical coma with no visible jets, no rotating outgassing sources, none of the typical signs of chaotic sublimation. The acceleration vector points precisely where it needs to for the Hill radius intercept. Natural outgassing produces random directional thrust. This was targeted. Consider the timing. The acceleration occurred during the telemetry blackout when precise tracking wasn't possible. Not before conjunction when we could have watched in real time. Not after when we could have measured every detail. Right in the middle of our blind spot. Solar heating provides both maximum energy and perfect cover for any course correction. The object passed Earth on its way to Jupiter, close enough that any probe with basic sensors could have gathered enormous amounts of data about our planet. Atmospheric, composition, electromagnetic emissions, thermal signatures, all the hallmarks of a technological civilization broadcasting across multiple spectrums. Yet 3i Atlas did nothing. No orientation changes, no thermal variations suggesting equipment activating, no unusual radio reflections. It flew past Earth like we weren't even there. This complete disinterest in Earth tells us something profound. If 3i Atlas is artificial, and that's still a hypothesis not confirmed by NASA, then we weren't the destination. We're just scenery on the way to somewhere more important. Jupiter makes perfect strategic sense as a target. The planet's magnetosphere is the largest in the solar system, a massive region of charged particles and magnetic fields that could power autonomous probes indefinitely. Any civilization that knows how to tap electromagnetic energy would see Jupiter as a cosmic power plant. You could run entire fleets of probes just by harvesting what Jupiter generates naturally. The Hill radius offers more than energy. It contains Lagrange points, specific locations where gravitational forces balance perfectly. The L1 point sits about 50 million kilometers from Jupiter between the planet and Sun. An object there can observe both the inner solar system and Jupiter without ever changing position. The L2 point sits on Jupiter's far side, perpetually hidden in the planet's shadow from Earth's perspective. Perfect for parking hardware you don't want detected. Within this gravitational framework, autonomous probes could position themselves for centuries with minimal station keeping. No complex maneuvers, no fuel burned fighting perturbations, just celestial mechanics maintaining position naturally. For any civilization thinking on thousand-year timescales, this is how you build lasting infrastructure in a foreign star system. Some researchers propose what they call sentinel theory, though this remains unconfirmed speculation. The hypothesis suggests advanced civilizations don't send massive ships or single probes to explore other systems. They send carrier craft containing dozens of smaller autonomous units designed for long-term monitoring. The carrier approaches a stable region, like Jupiter's Hill radius, and performs a dispersion event. The smaller probes spread across strategic points throughout the system. If this hypothesis were correct, we might see what appears to be a fragmentation event as 3I Atlas crosses into Jupiter's domain. Not an explosion, just the parent object separating into multiple pieces that then break and move toward different destinations. Some heading for L1, others toward L2. A few perhaps diving deeper toward Jupiter's moons. From Earth, it would look like a natural comet breaking apart. The individual objects would be too small and dark to track, operating in radiation environments that make detection nearly impossible. Jupiter's radiation belts create another advantage. While lethal to biological organisms, the high-energy, particle flux actually protects against detection. Radio signals get scattered by plasma in the magnetosphere. Optical observations struggle against auroral background glow. If you wanted to hide electronic signatures from primitive civilizations in the inner system, Jupiter's radiation environment provides natural jamming. The view from Jupiter is ideal for surveillance. You're far enough out to see the entire inner solar system spread before you. Earth, Mars, Venus, Mercury, all visible and trackable. Radio emissions from Earth wash over your position constantly. You have a front row seat to everything happening in the warm inner orbits where complex chemistry creates conditions for life. Meanwhile, you're sitting where nothing biological could survive, meaning no organic civilization will come investigating your equipment anytime soon. 3I Atlas joins a pattern of interstellar visitors that keeps getting stranger. Oumuamua in 2017 showed bizarre characteristics: extreme elongation, unusual reflectivity, acceleration without visible outgassing. Avi Loeb from Harvard proposed it might be a light sail, though this remains highly controversial. Then came 2I Borisov in 2019, which looked reassuringly normal with a proper coma and typical comet composition. Now 3I Atlas somehow manages to be more unsettling than Oumuamua, despite appearing more comet-like. It has a coma and shows activity, but the trajectory precision and acceleration timing raise questions that natural explanations struggle to answer. Some researchers suggest it's like someone learned from Oumuamua's obvious anomalies and designed the next probe to blend in better while still accomplishing mission objectives. This remains speculation, but the physics supports certain possibilities. Light sails pushed by radiation pressure could cross interstellar distances without engines or fuel. Hollow body designs, maximizing surface area while minimizing mass, would be easier to accelerate and harder to detect. Fractal geometries creating enormous effective surface areas within compact volumes. These aren't fantasy concepts. They're designs we'd consider for our own interstellar probes. The truly uncomfortable question is whether 3I Atlas is alone. Statistical models suggest many interstellar objects pass through our solar system undetected. Small, dark objects moving through the outer system could slip past unless they happen to reflect sunlight at just the right angle. We find the bright ones, the large ones, the close ones. How many others are we missing? Recent advances in astronomical observation make this question urgent. Artificial intelligence now analyzes telescope data, finding patterns invisible to human observers. AI systems detect thousands of microflares nightly, brief brightenings lasting less than a second. They spot microlensing events from tiny objects moving at unusual velocities. They catalogue transient objects that appear for minutes or hours, then vanish. Most of these detections have natural explanations, but some show characteristics researchers privately describe as troubling. Objects with velocities between normal solar system speeds and escape velocity. Brightness variations suggesting highly polished surfaces or unusual geometries. Light curves that don't match rock or ice or known materials. The Vera Rubin Observatory in Chile will photograph the entire visible sky every few nights. The Euclid Space Telescope is mapping while cataloguing everything that moves. The Nancy Grace Roman Space Telescope will conduct microlensing surveys orders of magnitude more sensitive than current capabilities. Each feeds data to AI systems designed to find anomalies. Some research teams have detected things they're not publishing. Not from conspiracy, but because the detections are too anomalous to present without confirmation. When AI flags something genuinely weird, a microflare from empty space or a transient moving at 2% light speed or a lensing event suggesting impossible mass, researchers wait, they check, they verify. Meanwhile, the anomaly sits in databases, flagged but unannounced. There are whispers about fast movers, objects tracked by multiple telescopes showing velocities inconsistent with natural solar system objects but below escape velocity. Not fast enough to be interstellar, not slow enough to be captured, just weird intermediate speeds requiring unusual trajectories. Some think these are classified satellites, others aren't sure, especially when objects show tumbling or unusual shapes. The timing matters. 3I Atlas arrives as our observational capabilities undergo exponential improvement. We're suddenly seeing things we couldn't before, and what we're seeing is stranger than expected. Maybe that's coincidence. Better telescopes naturally find more weirdness. Or maybe we're finally noticing things that have always been there, invisible until we built machines smart enough to spot them. If 3I Atlas represents intentional activity, if it's deploying probes while we watch, then every anomalous detection could be evidence of presence we're only now recognizing. Two curves intersecting, their arrival or activation, and our developing ability to see. Meeting at a point that feels less like coincidence and more like synchronization. Academic debates continue about the mathematics. Small uncertainties in initial observations get magnified when projecting trajectories across interstellar distances. An error of 0.001 degrees becomes millions of kilometers by Jupiter. Skeptics argue the Hill radius intercept might not be as precise as it appears. Different orbital models produce different predictions. We won't know definitively until 3I Atlas actually reaches Jupiter. But the pattern is there. The precision approach, the acceleration during conjunction, the complete disinterest in Earth, the targeting of Jupiter's most strategically valuable gravitational region. Each piece could have a natural explanation. Together, they paint a picture that's difficult to dismiss. NASA maintains 3I Atlas is a natural comet. They point to the lack of radio emissions, the absence of clearly artificial signatures, the consistency with known cometary physics. These are valid points. The scientific method demands defaulting to natural explanations until evidence conclusively rules them out. Yet, as trajectory refinements confirm the Hill radius approach again and again, uncomfortable questions get harder to dismiss. At some point, coincidence stops being satisfactory. You have to consider alternatives that challenge assumptions about our cosmic significance. Because if something out there is building infrastructure around Jupiter, we need to understand what it's for. More importantly, we need to know why they're building it right next door. The deployment might already be underway, hidden in radiation and distance, establishing networks we won't detect until they choose to announce themselves. Our solar system might never have been as empty as we believed. We might be surrounded by architecture mistaken for nature, probes catalogued as comets, signals dismissed as noise. And 3i Atlas, with its surgical approach to Jupiter's Hill radius, might not be an isolated visitor, but the first one we noticed in a crowd we're only beginning to see. The data keeps rolling in. Every observation brings us closer to understanding what we're actually looking at. Whether natural phenomenon or something more deliberate, 3i Atlas is teaching us that the universe doesn't always behave the way our textbooks say it should. Sometimes precision appears where there should be chaos. Sometimes visitors pass by without stopping to say hello. And sometimes the most important events in human history happen not with grand announcements, but with subtle movements in the dark, detected only by those watching carefully enough to notice.